For our project, we chose to design and analyze a 90cc two-stroke single-piston engine. The three components we chose to focus on were the piston head, wrist pin, and connecting rod. A pressure representing the force created by the expanding gases was applied across the entire top surface of the piston head. A fixed support was placed inside the hole that connects the connecting rod to the crankshaft. Additionally, a frictionless support is used to keep the piston fixed along the z-axis. Analysis is conducted when the piston is at top dead center, making this fixed support an accurate approximation of the reactions when the force is applied. The pressure applied was approximated as 700 psi, a typical max pressure experienced by low compression engines. The two passing criteria were the von Mises stress below the maximum that allows for a 500 million cycle life, a buckling factor of safety above 1.5, with a mesh consisting mostly of multi-node tetrahedrons. If the model failed either of these criteria, changes were made accordingly until it passed. The piston head and connecting rod were given the properties of 201.0 T7 sandcast aluminum. The wrist pin was given the properties of 4340 alloy steel. The original stress plots indicate that the highest stresses, having a magnitude of 40,000 psi, was located along the edge where the piston head connects to the wrist pin. The stress here is well over the fatigue stress limit of 14.2 ksi. The stress plots for the original model show a maximum stress of 44,000 psi, which is nowhere near the endurance limit of 100 ksi. For the original connecting rod, the ANSYS model indicates that the maximum stress is approximately 52,000 psi, meaning the part fails both yielding and fatigue criteria. Buckling analysis was also performed on the assembly as a whole. The plot shown is the first buckling mode. As you can see, the connecting rod is the first component to fail, with a buckling mode multiplier of 0.72. This is to be expected, as the connecting rod is the slenderest component in the assembly. After several geometric revisions and subsequent analysis were performed, the following final geometries were created. Here is a side-by-side comparison between the original and final design. The major difference between the two models is a 0.0625 fillet radius inside the wrist pin channel. In addition, the hole size was increased in order to decrease the stress in this area. ANSYS shows that making these two minor changes reduces the maximum stress from 40,000 psi to 12,000 psi, bringing the maximum stress below the fatigue stress limit of 14.2 ksi. Because the connecting rod failed both the fatigue criteria and the buckling factor of safety, its geometry changed the most. Like the piston head, the radius inside the wrist pin channel was filleted with a 0.0625 inch radius. The fillet, where the shaft meets the cylinder, was also increased to reduce stress in these areas. The combination of these changes reduces the maximum stress from 52,000 psi to only 13,000 psi, bringing the maximum stress below the fatigue stress limit. In order to prevent buckling, the thickness of the shaft was increased to 0.312 inches. After reevaluating buckling, the new first mode was found to have a buckling mode multiplier of 6.7, well over the minimum buckling factor of safety. In conclusion, the original approximations of geometry were not too far off, making only minimal changes to the piston head and wrist pin. While we were able to bring the stresses below the minimum fatigue and yielding requirements, the major source of stress were singularities located at component interfaces.